So let me introduce myself. Uh, I'm Dr. Mahendra Gattu. I'm currently working as assistant professor in Department of Civil Engineering at NIT-Rourkela. I have done my bachelor's in civil engineering at IIT Madras and master's in civil engineering at University of Virginia. And then I did my PhD at Northwestern University. I have worked in L&T, and then I joined BIT for a period of 1 year, and then I joined NIT-Rourkela, and I have been here ever since. So I will go through this presentation, uh, which where I will tell about my research work done in the fracture in composites, aluminum alloys, and epoxy resins. So, is my voice audible? Is it clear to you?
Yes, sir.
Yes.
Okay. Yes. Continue. So, so here is the outline of my presentation. Since October 2017, I am carrying out research in the area of fracture mechanics. I'll present my research describing the experimental work on composites, specifically on effect of loading rates on fracture properties. Then I will tell about experimental work done on aluminum alloys, and I will describe how the fracture toughness was calculated and crack growth resistance curves are calculated in aluminum alloys. So in the last around 2 years, I'm studying fracture in epoxy resins, which are used to bind the composite materials. So these epoxy resins can be toughened to make it more stronger, and this toughening can be done using carbon nanotubes or using nano alumina. So I have studied both these uh, reinforcements, effect of both the carbon nanotube reinforcement and nano alumina reinforcement in epoxy resins. So, and in currently, currently in future, I will be working in, I'm working in fracture in viscoelastic materials. So I wrote few, I'll go through some of the results in that area. So, so yeah, this topic I was supposed to pursue, but due to some thing I couldn't do it. Low cost digital DSE. And the acknowledgements, first I want to thank my PhD students who did the experimental work and helped me in doing the analysis. Ala Satyanarayana, he graduated in June 2022, and then Vice-Raj Rajasekhar, he submitted his thesis last December, and currently we'll be planning for the defense. And the from the Department of Civil Engineering, I got some very useful critical help from Shishir Kumar Sahu sir and Asha Patel madam for doing the experimental part. For help, she helped them. They helped me in the experimental part. So let me give a brief introduction of fraction mechanics and what exactly we'll be looking into when you study fraction mechanics. So we have here a uniform bar subjected to a tensile load, and you have studied in strength of materials. The relation between the stress and the strain is given as sigma is equal to E epsilon. And as you keep loading the material, at one point the maximum load, that is peak load, is reached, and the material and the structure will not be able to take more load. So sigma you can calculate for the peak load by dividing force by area. So this is for a material in which there are no inherent flaws, but most of the materials have some flaws. Flaws can be holes or cracks which are developed during the loading process. So what will happen if what will happen to the load carrying capacity, load carrying ability in presence of cracks? So this is the question we answer in fraction mechanics. So as we increase the load, what happens is the crack starts to grow, and uh, the material will not be able to take more load, and at one point it will fail, and we can find the peak strength. Okay. So if you do experiments, and what we find is, depending on the crack size, the residual strength reduces. Okay, so this is the relationship between crack length size in the material, the structure, and its peak load. So So as we keep increasing the crack length, the strength of the structure reduces. So this is this has been established experimentally. So without any crack length, we have our design strength that is given by the strength of materials. But in presence of crack, we have some reduction in strength. And usually, if the crack length size is say uh, less than this, between here to here, then for the design service load, the structure is safe. But if the crack length exceeds this value, then for the applied service load, it might fail. Okay. And if suppose the crack length is very large, so if you are in this region, then the material might fail even for normal service loads. Okay. So if the crack length is very large, then the material can fail even for normal service load because the residual strength drops with the increase in crack length. Okay. So in fraction mechanics, we provide a theoretical framework where we will look into the we look into the strength of the structure in presence of cracks. So this is what I want to convey from this slide. And fraction mechanics, the subject is an intersection of lot of fields. So depending on the length scale, that is depending on the size we are focusing on, we can have say atomistic fracture mechanics. So here we are looking into the fracture happening between molecules. So there is bond energy and interatomic potential and all. So there is atomistic modeling of fracture which can be done. And if you go to a little higher size, then we are looking into dislocations, material dislocations and grain boundaries. So here we are looking to this part is usually dealt with by material science people. And if you go to little higher size, then we have our stress strain quantities and we have the plasticity concepts which are used in describe metals, and we are in the applied mechanics domain. So, and if you go to the normal size, like which you see in the real world, then we are engineering side, we'll do the testing and all. And whatever tests we are doing in the laboratories, we transfer that information so that we can actually build the bigger applications. So say suppose you want to build a aircraft. So before actually building the aircraft, you do a test in laboratory and using the test information to design the aircraft. Similarly for buildings, if you want to build a column beam, you do a material strength testing at the laboratory level, and then you scale it up and find the strength of the structure at the actual real life. And same thing for the naval structures. So fracture mechanics is a intersection of lot of fields, right, from atoms to the actual real life applications. And it is not possible to know this entire field in one's lifetime, but we can hope to focus on certain areas and contribute to the field. So I'll now discuss about linear elastic fracture mechanics, which the basic idea in linear elastic fracture mechanics is that, so here I have shown a V-shaped notch. Actually, it is a very sharp notch. The width of the notch is not there. It's a very sharp notch, and I'm looking into the what is the stress field at this sharp corner. Okay, so this is called the crack tip, and what is the stress field produced in the crack tip. So there are some using theory of elasticity, we can find out what is the stress produced at the crack tip, and the stress is described in terms of the uh, polar coordinates. So we have our theta and r is the radial coordinate, and the stress in the is given like this using this formula is there. So Ka is the stress intensity factor, and it is stress is inversely proportional to 1 by square root of r. So as we at the crack tip we can expect infinite stresses according to linear elastic fracture mechanics theory. And as you move away from the crack tip, what will happen is the stress will drop down. And we have the Fij or theta term. So this is a geometric factor which is independent of the applied load. Ki is dependent on the applied load and Fij is independent of the applied load. So this is what, yeah. So Ki is proportional to the applied load. It is what is happening here is when you apply the load here, the crack will try to this material will this crack will try to open up. So there is this called mode 1 fracture, and so we have K1, that is a mode 1 stress intensity factor. And Fij is independent of the applied load and K is proportional to the applied load. So we can calculate what is the, just 1 minute. Sorry. Yeah. In fracture mechanics, there is a term called fracture toughness, which is used and what is fracture toughness, I will describe here. So we have our stress intensity factor Ka is sigma square root of pi a f of a by d. So f of a by d, this f of a by d function can be obtained from the stress intensity factor handbooks. Okay, and depending on the geometry of the problem, we can look into the stress intensity factor handbook and find out what is f of a by d and find the Ka. We can rewrite this equation like this also. We multiply and divide by square root d, and then we get square root of pi a by d times f of a by d, that we write as K of a by d. So in my analysis, I will be using this K instead of f. Okay. So sigma square root d K of a by d. Now, what is fracture toughness? When you keep applying the load, the crack will grow, and at certain point, the peak load will be reached. So we'll find out what is the K at that peak load. So instead of sigma is applied load, we put sigma is sigma u. So when you put the value sigma u, and then we find what is K, that K is called the fracture toughness, KIC. So KIC is the mode 1 fracture toughness. It is calculated from the peak load value. And during the testing process, as you apply the load, the crack length is increasing. So initially it will be A, and after the peak load, it will be A plus delta AC. So we have to substitute sigma is sigma u, and instead of A, we have to put A plus delta AC. And then a geometry factor, which you can obtain from the stress intensity factor handbooks or by numerical techniques. So this fracture toughness we can obtain by doing the experiment. So, but there is a catch here. Actually, in most of the laboratories, at least in our NIT-RKL, we don't have access to measure we don't have equipment to measure the crack growth. So what we have to do is we can only get the initial crack length, and we don't know what is the crack length of the peak load. So we'll be using our initial crack length while calculating the fracture toughness. And so this fracture toughness is called as apparent fracture toughness, because we are not actually finding out what is the crack length at the peak load. If you have equipment, we can find it out, and then if you can find out what is the crack length at peak load, then we get what is the real fracture toughness. So KAC with sigma is sigma u and A is A naught plus delta AC, we get the actual fracture toughness. So this is one point I want to make, because I will be discussing this again for some like in our laboratory, we without using the we are able to, without using any equipment, we are able to calculate the crack growth length at the peak load. So using our testing process. So I'll tell about that in future in the next slide. So this is about linear elastic fraction mechanics. So in linear elastic fraction mechanics was the first starting point where the field began, and then it later progressed to other areas. So what happens in linear elastic fraction mechanics is that there is some fracture processes happening at the crack tip. So the fracture processes we can divide into some zones. So one zone we can identify is the nonlinear hardening zone, where in that zone the material will give a hardening response. Okay, with the increase in stress or with increase in strain, the stress will increase. So that is a hardening aspect there. And you see the blue color dots, that is the softening zone. Softening zone is where the voids are created and also the material gets damaged. So in linear elastic fracture mechanics, these two zones are very small, negligibly small, and we can approximate them to be taking place at a single point at just near the crack tip. Okay. So this is one assumption. This is one main theoretical assumption for linear elastic fracture mechanics. So all the fracture processes which that are taking place happen at a point just at the crack tip. Okay, the size of this fracturing zone and non-linear hardening zone is very small compared to the size of the structure. So this is what non-linear zone is very small. Yeah, and the stress field, if you plot that Ka by square root of 2 pi r along this theta is 0 degrees. We have the stress field like here like this. So as we approach the crack tip, the stress shoots up to infinite value according to linear elastic fraction mechanics. But in reality, it is not like that. So we have to modify the theory a little bit to account for that. So yeah, so in metals, what happens is for metals we have scientists have developed the elastic plastic fracture mechanics. So in elastic plastic fracture mechanics, what happens is at the crack tip we have a zone of nonlinear hardening, which is this nonlinear hardening zone, and we have the softening zone. This nonlinear hardening zone is very large, and it dictates the crack growth and all. And softening zone is negligibly small compared to the nonlinear hardening zone. And what happens is, as we have seen, the stress at the crack tip shoots to infinity, but actually before it reaches infinity value, it reaches the yield stress, and the material will start to yield when in this region. Okay, so whenever the yield stress is exceeded, the material will start to yield, and we can find out what is the yielding zone at the crack tip. So if you just apply the formula, if you just apply the formula, sigma y is equal to Ka by square root of 2 pi rp, we get the rp value as 1 by 2 pi Ka by sigma y whole square. However, if you go a little deeper into it and find out that if you do a force balance of the ligament length, ligament is the uncut portion. If you do a force balance of the ligament length, then we have to adjust this rp value so that it is twice the value, and this force which is developing will balance out will take care of the force equilibrium in the vertical direction. Okay, so actual plastic zone size is calculated will be 2 rp, and so 2 rp is 1 by pi Ka by sigma by whole square. This theory of elastic plastic fraction mechanics is applicable to ductile materials and also tough alloys. And now the field I will describe is this field of quasi-brittle fraction mechanics. So quasi-brittle fraction mechanics are quasi-brittle materials. The characteristic of quasi-brittle materials can be described here. What happens is that most of the engineering materials are quasi-brittle. For example, concrete, composites, polymers, bones, and many other engineering materials come under this category. And the theory of quasi-brittle fraction mechanics has been accepted by the American Concrete Institute, and they have there's a committee ACI 446. They have recommended quasi-brittle fracture mechanics based design. At least in Shear, they have accepted that theory, and they have included in the code in 2020. So after a lot of research and a lot of debate, finally they have accepted this quasi-brittle fracture mechanics. So it is a very important concept to know for all the civil engineers who are involved in design of concrete structures. So what exactly is quasi-brittle fracture mechanics? So at the crack tip, what happens is we have, as I said, for metals, we have a non-linear hardening zone and a softening zone. For concrete, this non-linear hardening zone is very small. It is compared to the softening zone. Softening zone is very large. Okay, so softening zone, as I was saying, it consists of micro cracking, void formation, and interface breakage, and frictional slip. Frictional slip means aggregate frictional slip can happen. Void formation means creation of voids, and micro cracking means small micro cracks which will coalesce and become a larger crack. So, and interface breakage means breakage between the matrix and the aggregate. So all this come under softening. All this gender are called as softening. And this softening zone is very large compared to and it can be compared to the size of the structure also. Okay, so this is one of the key concept in quasi-brittle fracture mechanics, the presence of a large softening zone. Okay. And if you do as I was saying, the concrete composites and all, yeah. And what happens here is the zone of softening is will exceed the plastic zone size for metals. So the R value, I think here the symbol is not there. R value is very much higher compared to the plastic zone size in metals. So this is the one key concept which I want you to take home from this presentation. So for quasi-brittle fracture mechanics, we have developed one model called the equivalent elastic crack model. So I will describe a little bit of mathematics, and hopefully you will be able to appreciate it when I present the analysis of the experiments. So what happens in quasi-brittle fracture in this equivalent elastic crack model is we have here A naught. A naught is the initial crack length before a load was applied. And as you keep applying the load, the crack length will increase. Initially, the fracture will start to happen at the crack tip, and we'll have small micro cracks, and those micro cracks will become larger cracks, and finally we can see a physical crack that is materially separated. Okay, and so at the peak load, we can see some physical crack here, and also at the crack tip, the crack tip has moved from this point to this point, and we are now seeing a fracture process zone size, which is shaded, which is a shaded region. So this is what is happening in reality. Okay, so there is this initial crack length, there is this physical crack, and also there is a at the new crack tip there is this fracture process zone. Okay. So let's say that tip of the fracture process zone is S, the tip of the physical crack is T. Okay, so for analysis purpose, what we do is at the peak load, we approximate this fracture process zone and the physical crack by this stress distribution. So we take the initial crack length and then the physical crack and then the softening zone. So whatever softening is occurring, softening means the peak stress is reached and there is a drop in the stress value. So let's say sigma S is the peak stress, and then between S to T, there is a drop in the stress value, and S to R, the stress will reach to sigma nu here at this point. So what we do is this region of stress distribution is very complicated, and for analysis purpose, we simplify this stress distribution diagram by a LEFM diagram like this. Okay, so all the fracture processes which are happening between ST and delta AC in this entire region, we approximate it to be one physical. We approximate it to be equal to delta A equivalent. Okay, so delta A equivalent is somewhere between delta AC plus some small length. Okay, so we are what we are doing is we are approximating all the fracture process to be lumped into this physical crack delta A eq. And beyond that, we will assume the LEFM equations, linear elastic fracture mechanics equations. Okay, so this is one of the this is a basic of the equivalent elastic crack model. So whatever all the fracture process which is due to the physical crack and the fracture process zone, we are lumping it into one single crack, physical crack of delta AQ, and beyond that we are using the LEFM criteria. So in that case, the formula which you have developed for LEFM is applicable. So the fracture toughness KAC is sigma nu square root of D K of A naught plus, instead of delta AC, which was actual physical crack, we have the delta AEQ, the equivalent crack length. So it is this delta A naught plus delta AEQ is called the equivalent crack length, and hence the name equivalent elastic crack model. So we'll be using this equation to analyze analyze the experimental data. So I just want to present you with this, and what we see is that
Yeah.
D is a any questions? Yeah. So what you see is that we have the structure size D. Just one. Yeah, I think I'll continue. Yeah, I'll continue. So yeah, what? Yeah. So we have the structure size D here, So as the structure size increases, so we'll say that it is becoming size of the structure is becoming large, and as then what happens is that this delta A equivalent or whatever this delta A equivalent will approach one value called CF. CF is called the material characteristic length. So for very large structure, means for infinite size structure, this delta AQ will stabilize and it will reach one critical value called CF. Okay, so this will be a material property. Okay, so for a very large size, whatever fracture, the maximum possible fracture position which you can develop, that is the CF, and that is called material characteristic length. And yeah, so we can simplify the equations of this equivalent elastic crack model. So we have the KIC, we are squaring the term, and K naught square is a function of alpha naught plus CF by D. So for large size, we are just putting delta A equivalent as CF. And here we do a Taylor series expansion. So if you do a Taylor series expansion, we have uh, f f of t will be f of x plus del x will be f of x plus f derivative of del x. So here k naught square, so k naught of alpha whole square, which is denoted as k naught square. So that is what I'm writing here, k naught of alpha naught, which is k naught square, and derivative of k naught of alpha square is 2 k naught k prime. So that is what I'm writing, and the delta x value is CF by D. So this is a simple Taylor series expansion we are doing for the KC square. And then we are rearranging our equations, and how we are rearranging, we are sending the 1 by sigma n square term to the left hand side and 1 by KIC square term to the right hand side. So we are getting something like this. So left hand side we have 1 by sigma nu square, and we have k naught square by KIC square, and 2 k naught prime by k naught by KIC square. So here we have a function of the form y is equal to mx plus c. So this is m, x value will be d, and this is the intercept term capital C. Okay. So we'll be using this equation to analyze the experimental data. So the basic equation, we are doing a Taylor series expansion, and we're getting this, and we have the data for peak load and the size, and using that we can find out this slope and the intercept. Okay, once we know the slope and intercept, we can calculate KIC and CF value. Because K naught and K naught prime we can calculate using FEM or the stress intensity factor handbooks. From there we can get that. So this is the basic gist. This is the equation which will be used to analyze our experimental data. So, or we can rewrite this equation in another form. We can bring our d term to the left hand side denominator here. So in that case, we have y2 is equal to m2 x2 plus c2. So here m2 value is this one and c2 value is this one. Y2 is different, 1 by sigma n square d, and x2 value will be 1 by d. Okay. So we can use either of this, and both the results are almost are close. And so I written some FEM code which simulates a quasi brittle material, and if I calculate the peak load and using that FEM code for different sizes, size of 20, I think 20, this is 10 units, and 40, 60, and 80. I have calculated the peak load, and then I plotted 1 by
Hey, hi
T
Mahendra.
plus.
I was busy in meeting. I joined just now. Sorry for excuse.
Who was speaking, sir?
Sai speaking here.
Oh, okay, Sai Krishna. Okay, nice meeting you.
Yeah, I
Nice.
was busy in other stuff. I just joined. I just got a guest. I don't know. I forgot other your previous data.
Okay,
Okay.
thank you for joining. It was yeah, Sunday time. I'm actually recording this video so that if in case I can send it to the participants.
Yeah,
And
point taken.
so I'll
Thanks.
continue.
Yeah, you can continue.
Yeah. So basically, I have written some FM code where I can. So where I have calculated the peak load values for different sizes, and I plot this 1 by sigma square on the y-axis and d on the x-axis. D is the size of the structure, and I can see that the quasi-brittle simulation is means the quasi-brittle curve is coming. This 1 by sigma square term is there on the x-axis, and D term is on the on the sigma square is on the y-axis, and D is on the x-axis. So we can, if you find the slope of this,
What is
slope
the
of this is
I have a question. What is the
yeah.
simulation you have used for calculation this?
I have used a cohesive crack model. So in a cohesive crack model, we model the material by using a traction separation law. Okay. So actually,
Sorry?
there is a traction separation law. So I
Okay.
think you have missed the previous part. So I'll just go through that. So here, what is happening here is at the crack tip, there is a fracture process happening. Fracture process means material is breaking up. Okay. And
Hmm.
material breaking up means the material load carrying capacity is getting reduced. Okay, so this ligament, this region, we can model using a cohesive crack model. That means that the peak stress has reached in this region and the material has started failing, so the load will drop down. Okay, so that load dropping down is actually shown here. So the maximum stress which material can take is here, and beyond that, when you keep loading it, the material is softening. So this is the softening part.
But
So
at a
this
point, the load fluctuates, right?
no. Crack at the crack tip, fracture is happening. Means the material is breaking up.
We are talking
So
on that fracture, but that
uh,
fracture is not at a point. It might even, elongate or something to like that.
yeah. That is what I'm saying. This is the fracture process, Joe. That means in this region, fracture is occurring everywhere. But within this
Okay.
region, certain part of the region is fracture is more. So its load carrying capacity is very
Oh,
less.
okay. You are talking within the boundary. Within the boundary of a crack, certain
Mhm.
part might be a, that is what you are calculating, right? Yeah.
Yeah. So if you see here, this region it is uncracked. Nothing is happened here. So the peak load has not yet been reached here. But at the crack tip, the peak load has been reached, the material has broken down, and then the load carrying capacity has reduced. So actual load carrying capacity is this much only in this region. If you just near the crack, it is very less. Okay. And if you see the physical crack which has developed, there is zero load carrying capacity in this. So initially the crack was here, and as it progresses, this is a physical crack which has formed during the loading process. Okay. So in this region, there is the material cannot take any more load. Okay. So this part, but in this region, it can still take some load, and that is represented by this stress strain diagram, stress diagram. And in FEM, we can use a something called traction separation law. So depending on the crack opening which is happening here, crack opening displacement which is happening here, we can find out what is the stress in that region. Okay. So larger is the crack opening, more is the drop in stress. So we can simulate that in cohesive crack model, and I have done that in FEM. I'm not showing the details on all that. So just for illustration, I'm just saying that if when you do FEM analysis also using the traction separation properties of the material, we can simulate this quasi-brittle property, quasi-brittle equations. Okay, the equivalent elastic rock model. So FEM simulations, we can get sigma value and D value, and if you plot it, you get a curve like this. And the slope of this line is equal to k naught square by KAC square. And we can find out what is this KAC value, which is a fracture toughness. And from the intercept is this one. From this intercept, you can calculate this value. We already know KAC. So from that, we can get the CF value, which is the material characteristic length. So these two fracture properties we can determine. This is done using FEM, but we'll do experiments. We'll get the similar results. Okay. So this is linear regression analysis too, and from there we will get the KAC and CF value. So CF value is 22.6 millimeter, and KAC is 1037.1. The units are Newton joule per I think Newton per millimeter power Newton millimeter power 3/2 something like that. Yes, so with this basics, let's simplify this equation further, and we get in a form which I hope you can understand. So this is the classical. I'll describe about the Boson size equation. So the two linear regression analysis equations are obtained from the Taylor series expansion, which is shown here. KC square sigma n square d. You have k naught square.
Oh,
K naught derivative, which is 2 k naught from k naught. This equation can be recast in this form. Okay, so we write sigma nu as BFT by square root of 1 plus d by d naught. Okay, so this is the size effect equation which is developed by Professor Bajant at Northwestern University in early 1980s. So what does this equation mean? So here on the left hand side we have the strength of the structure, okay, sigma nu, and on the right hand side we have a denominator term, there is 1 plus d by d naught. Okay, so d is the size of the structure. So the size of the structure is d, and d naught is a material property. Basing on it is a function of material characteristic length. And BFT, you can think it as when size of the structure is 0, we get sigma nu is BFT. So if you plot this equation, sigma nu and d by d naught on x and y axis, you'll get something like this. So we have this equation sigma nu by BFT here, and we're taking a logarithm of that, plotting it here. And we have log of the denominator, which is log of d by d naught here, that is plotted here. So if you see here, we have from the FEM equations, from the FEM solution, we have that sigma nu by BFT, which is sketched here. All the data points are sketched here. So we are seeing that as a size of the structure. Some noise is there, so I have to mute that. Yeah, I think I'm muting it. Yeah, I'm muted. So I think I'll carry on. So we have the thing we have to observe is that with this here on the left hand side here, if you see the structure size is small, and as you move along this axis, the structure size is increasing. And if you see here, if you move from here to if you move from this axis in the upward direction, the strength will increase. Okay. So what you're seeing here is a structure with a smaller size has a higher strength compared to a structure with a larger size. Okay, so this is a larger size structure, and its strength is less compared to a structure with a smaller size. So we are seeing a size dependency of strength for quasi-brittle materials. So what we have studied in mechanics of materials, we say that we calculate our sigma peak value for a given size in the laboratory, and then we use that peak stress value for design in the actual real life structures. But from the theory of quasi-brittle fracture mechanics, we see that for larger size structures, the strength is less compared to a smaller size structure in the presence of cracks. In presence of cracks, we see that there is a size dependency of strength. So in case you test usually laboratory tests are done for small size, so you determine the strength there. And if you use that strength for design of real life structure, then the actual strength of the structure is smaller compared to the laboratory test. So you might be that will be a wrong design. Okay, so you have to account for the reduction in strength, and so here the quasi-brittle fracture mechanics will come into picture. So this theory has now been accepted, as I was saying earlier, that American Concrete Institute has accepted this theory, and they have started using this size dependency. So if you refer to the ACI code, there's small changes which are come, which use these sort of equations. So so this is the strength criteria. So for smaller sizes, we have the strength criteria, and for the larger sizes, we have so for smaller sizes, as t approaches 0, this term will become sigma nu will approach BFT, and for larger sizes, as d approaches a very large value, then we can neglect our one. So sigma nu will be inversely proportional to the square root of d, 1 by square root of d. Okay. So we have for larger sizes a LEFM criteria. So here the sigma stress will be scaling with respect to 1 by square root of d. And for smaller sizes, there is no scaling happening. We have whatever strength is almost like approaches BFT. So this is the theory of quasi-brittle fracture mechanics, and there is something about R curve, crack growth resistance curve, which we can, I think, might not be possible to explain, but I'll see. So here we have the expression for the uh, fracture energy Gu, okay, uh, which is given as KSE square by E. So KSE we can use that equivalent elastic crack model and put sigma n square d k naught of alpha naught plus delta A by d whole square. So if you plot this fraction energy curves for as a function of crack length for a given size, for a given size d, you get one curve, and as size increases, you get uh, another three more curves. So I plotted it for four sizes, d1, d2, d3, d4. So this is the fraction energy curve as the crack length is increasing. Okay. So initially we have a crack length, and then as crack length increases, this is the fraction energy which is dissipated. Now the R curve is called a crack growth resistance curve. The unique property of R curve is that it touches all these GU curves. Okay, it touches means it touches all these curves and touches only at a single point. Okay, so there are two conditions it will satisfy. One is it touches these curves and it touches at a single point. That means the at that point of intersection, the slope of the R curve will be same as slope of the GU curve. Okay, so effectively it will look something like this. So this is the crack growth resistance curve. So it touches the each of the GU curves at a single point, and since it touches a single point, these two equations will be valid. So this is a intersection criteria, and this is the tangential criteria. Yeah, so using that, you can use a numerical approach to plot the R curve, or you can use a you can use the analytical approach also to find out the R curve. So all this we will do. This is the theory which I present now, and then we'll go ahead with the experiments. Okay, so first, initially when I started this topic, I had to learn all the basics of the fraction mechanics, and then I began the experiments with Satyanarayana, my first PhD student, and we started with this composite material. So I think on Friday, many of you attended the presentation by SK Sahu sir, who has been working on this composite materials. So he was telling about glare. Glare is a glass fiber plus alumina, which is used in aerospace industry for building aircraft. So Boeing and all, they're using it. So the glass fiber usually it's a bidirectional fiber, and this bidirectional fiber is binded by a matrix. Matrix is something like a gum which will join these fiber sheets. So for our experiment, we use this epoxy resin diglycidyl ether of bisphenol A, and for hardener we use this triethylene tetraimine. So the process of making the glass fiber, we did like this. We use a manual layup, manual process called hand layup method. And what we do is first we place a silicone sheet, and then we spray a non-sticker on this sheet, a plastic sheet. We spray this silicone, and which is a non-sticker, and then we place our glass fiber on top of that, and then we pour some epoxy resin, and then we spread that epoxy resin uniformly using this roller. After that, once the resin has spread uniformly, we place another layer, and then we roll it up on that first layer, and then we add some more resin and repeat the process. Okay, so we can target 8 layers or 16 layers like that, depending on our requirement. And once we get our required thickness, uh, what we do is we allow the curing to happen for around 3 days, and then we'll get the plate. Okay, so this is the plate which we will use for our mechanical testing. So we can cut this plate and find out test. We can prepare a test specimen, and then we can do some mechanical testing in our machine. So here we see a picture of the test specimen, and we are introducing a notch here. Notch is a crack. This is a blunt notch because the width of the blade is very large. So using a blunt notch, we did it. But later we realized that we should use a very sharp notch. But initially, we use a blunt notch crack, and then we did our experiments on this. So this is a glass fiber specimen, and we did our experiments on this one. This is the crack which we have created in the glass fiber here. So the experimental program we did when we started this research was like this. We had a scaling of the size of 3 is to 4 is to 5. So 30. So we made geometrically similar specimens. So what do you mean by geometrical similarity? A by D ratio, we have fixed it to be around 1 by 4, and L by D ratio we kept as 4, and then we varied the D value 30, 40, and 50. Okay. So A by D for all the specimens will be same, L by D for all the specimens will be same. The size of the specimen will change from 30, 40, and 50. So that is what we did. And for each set of A by D ratio and D1, D2, D3, we did give a different loading rates. So here we are gripping this material in a machine. So this is the grip length, and we are applying the loading rate. So loading rate can be you can give the load at which rate at which load is applied, or rate at which the displacement is applied. So we are giving a displacement loading rate. So here along this edge and this edge are expanding at a rate of 1 millimeter per minute. Okay, or we can make it this edge and this edge are expanding or separating at a rate of 10 millimeter per minute, or 100 millimeter, or 500 millimeter. So we did all these three rates. So there's a large change in the loading rate here from 1 to 500. And this we casted around 3 specimens for each geometry, and for each geometry we did 4 loading rate tests. So in total we have tested 180 test specimens, and that was for 0 means there is no notch, and A by D is 1 by 8, 0.25 is 1 by 4, 0.375 is like 3 by 8, and this is 4 by 8, which is 1 by 2. So all this we tested. And for material property calculation, we tested this specimen with no notch, and we got the Young's modulus value for different loading rates. So for 1 millimeter loading rate, we got 11.1 gigapascal. For 10, it is 13.7. 100, 14.38, and 500, it is 13.9. So since it's a bidirectional fiber, the fibers properties in this direction are almost same. So so we have EYY is also EXS. And to find shear modulus, we have to test this specimen in the 45-degree angle, and we got E45 and E45 values, and then we use one formula for GXY, which is based on the transformation of the stresses. So Q transpose sigma Q will be sigma prime. So using that, we get a formula, and then basing on the formula, we get the GXY value. Okay, so we can find out what is the GXY from E45, EXX, and EY. Poisson ratio we're assuming based on earlier studies. So this is our GXY properties, and so this is the data, experimental data, which we get for each loading rate. So here we have 1 millimeter loading rate, 10 millimeter, 100 millimeter, and 500 millimeter. What you're plotting is the peak stress values on the x-axis, on the y-axis, and the A by D ratio on the x-axis. So A by D means the notch depth by the diameter, by the size. It is shown on the x-axis here. So what we are seeing here is with increase in the crack length, the strength is reducing. So this is what we have at the beginning slide I have put. I told that if there is a crack length is increasing, then the strength of the structure is reducing. So that is what is clearly seen here. Increase in the crack length, the strength of the structure is reducing. So that is clear. And second thing we observe is, you see here, the red dot corresponds to size 30, square corresponds to size 40, and this triangle corresponds to size 50. So we can see that the red circle is lying above the blue square. That means the size 30 has a higher value of strength compared to size 40, and size 40 has a higher value of strength compared to size 50. So we are actually seeing a size effect in the experimental data. So the smaller size is having a higher strength, and the largest size, which is a triangle here, is having a smaller strength. Okay, so size effect is also being observed in the from the experimental data. Okay, so with this we can apply. So we are sure that there is some size effect, and there is this composite will follow a quasi-brittle fracture mechanics criteria. So we do our linear regression analysis, and we get we use that equation, and we see the data here. So I'm plotting 1 by sigma square d k naught square and 2 k naught prime by k naught 1 by d. So I'm using the linear regression tool, and I'm plotting it here. So this trend I'm getting, and I can put a I can have a plot of a straight line y is equal to mx plus c. So from the intercept and from the slope, we can find out our KAC and CF values. Okay, CF is coming around 8 millimeters and KAC 1122.69. So this is for loading rate of 1 millimeter per minute. So displacement loading rate. And for displacement loading of 10, we're getting some data like this. So the CF value is going to almost 0, and KAC we're getting a lesser value, 742. For size for loading rate 100, we're getting this trend, and loading rate 500, we're getting this trend. So what I do is I can calculate the KAC square by E value, which is the fracture energy. Okay, so and I plot that fracture energy in the plot. So, so for orthotropic material, the fracture energy calculation, we use these equations. We introduce one parameter lambda, and then we calculate this rho value, and then we calculate the homogenizing modulus E star, and then we get this GF, which is KAC square by E star. Okay. So using this, if you plot the fraction energy, so we have fraction energy here on the x-axis, on the y-axis, and loading rate, logarithm of the displacement loading rate. So 10 power 0 is 1, 10 power 1 is 10, 10 square is 100, and 10 cube is 1000, and 500 is somewhere in here. So red circle is the GF. So we have initially at loading rate 1 a high GF value, then it is reducing at 10, and then again it is increasing and increasing and reaches this value. Similarly, the CF, which is the fracture process zone size or the material casting length, also it follows this trend. Initially it is increasing, it is high, around 5 millimeters, and then it goes to 0, and then it is around between 1 and 2, and after that it is between 3 and 4. So this is what we observe. So we want to understand why this is happening. So to understand that, we look at the SEM imaging, that is the scanning electron microscope images of the failed specimens. And what we found was between 1 to 10 and between 10 to 100 and 100 to 500, the mechanism of failure in the composite material was different. Okay. So at these higher loading rates, say from 10 to 100 and 100 to 500, we found out multiple failure mechanisms, and the fibers in the lateral direction, that means perpendicular to the loading direction, they also started to fail. As a result, the FPC size started to increase. Okay, so this was what we understood at that point of time. But now, after some years, like after some, this was done 1990, 2000, 2019. Now, at this point of time, I have some different idea about this. I think there is more like a viscoelastic contribution and all, which we didn't do at that time. But probably it might be a reason for this uh, change in CF and all. So, yeah. So we wrote our first paper using this data and basing on the SEM images for different loading rate. So we see that SEM images, which was done in our metallurgy laboratory. So we looked at the failure surface and see some fibers, fiber pullout, the fiber imprints, matrix microcracking, that is cracking in the epoxy resin, and riverline patterns in the epoxy resin. When we found out fiber breakage, that is fiber actually breaking out at this loading rate. And at higher loading rates, we are finding matrix fiber debonding, and there is a lot of breaking in the lateral direction. So if the load is applied in this direction, in the perpendicular direction also the fibers were breaking. So similar thing at 500 we also found there is a lot of matrix microcracking, means at very high loading rate. So this is what we reported to the journal, and the editors and reviewers accepted it. So we had our first paper together. And we plotted the size effect law here, which is sigma nu BFT by 1 plus square root of d by d naught. So again, the strength criteria we are plotting here, and the LEFM criteria is here. All the experimental data are shown here for 180 test specimens. So you can see for loading rate of 1, the it is the cluster data is close to the strength criteria. And then at loading rate 10, there is a data is moved here. The experimental data is close to the LEFM. So we are seeing a sudden reduction in the fracture precision size. Okay, initially, the fracture precision size is nearly throughout the structure, and then suddenly there is a drop. So that's why we have a LEFM criteria. So all the fracture process is taking place at a point. So this is the LEFM criteria. And again, as we increase the loading rate from 10 to 100 and 100 to 500, so these experimental data points move again along the curve towards the strength criteria. So we are moving towards the strength criteria now. So 10 to 100 and 100 to 500. So at that point of time, we thought that this was due to some loading rate effects, but I'm right now I'm thinking that there could be viscoelastic effect, which we have not studied at that point. We didn't study in detail there. So now I'm looking into that aspect. I think I have spent over 1 hour now. Uh, shall we continue, or I think it's a good time to end the presentation? So our audience are able to follow what I was presented till now. Or if you have any questions, you can ask. Or if you're tuned out, I probably might end the talk. So any questions from the audience? Ipsita, madam, are you here?
Yes, sir. Yes, sir. Yeah.
Yeah, you
Just
want
going. Yeah, I'm just going through the slides.
if you, I mean, there are some more slides I can present for another 1 hour, but I want, means we can stop here also, and I think I might have conveyed all what I basic gist of my experimental program related to fracture here. So if you have any questions, I'll take, and probably I'll end it here. Probably I have given the flavor of what I'm doing. Uh,
So regarding the scanning electronic SEM images, scanning electronic microscope